this video, I want to talk about how we actually develop our learning objectives. So imagine you've got your Big 10 learning goals for your course as a whole. Now, how do you translate those into the objectives for specific topics? So for instance, we've got some big course scale goals like recognize the value of statistics and scientific research. Then when we're learning about t-tests and significance values, we want to make sure to tie what we do in that unit to that bigger course goal. So one of the things that's important to do then is to break down what it means to learn about t-tests and significance. What does it mean to understand that topic? So I want you to think on your own. What might be difficult about breaking down or unpacking a topic into specific learning objectives?
Hi, I'm Steve Pollack. I'm a physics professor engaged in research in the field of physics education. A manifestation of that difficulty with articulating learning goals is I usually find myself first writing the student should understand Newton's law. Saying the student should understand is immediately, it's a flag. When I write that down, it's a flag for me that, oh, that's not really a learning goal. That's a vague statement of an idea that I want. I know it. I know Newton's second law, and it's somehow become compiled for me. So it's just, there's a whole bunch of different elements, and separating them out into the pieces that build it up is not always intuitive for me anymore.
So one of the difficult parts of taking apart a learning goal and developing smaller learning goals is that as experts, we've forgotten what it's like to learn at these lower levels. We've forgotten the steps that we went through to go from these kind of more basic understandings to a more expert understanding. And so often what we do is we skip the steps. When we are out in the world and we're developing these understandings, through our experiences, we build these knowledge structures. And the knowledge structures, when we're novices, tend to be pretty superficial. We don't have really deep, well-connected knowledge structures. But over time, your knowledge structures become much more complex and rich, and the connections between ideas become much more implicit. So when you're breaking down a learning goal, it's hard to remember where are students at with this idea? What kind of knowledge and experience do they have around this idea that they can build from to be able to move to this more expert understanding?
So this is the idea of expert blindness, that sometimes we know something too well, and it's hard to remember how we learned it. So what are some strategies for going from our list of topics on our syllabus to creating some concrete learning objectives?
So one approach to going from that topic to learning objective transition is to start with the topic and then really think about and write down all of the concepts and ideas you want students to learn about that particular topic. They can be really little, they can be bigger, but just kind of get a whole list going and then kind of transition from that list into writing the learning goals.
So for example, if you're thinking about linear equations, you might think about, well, how am I going to have them understand the concept of growth? Because that's something that's really complicated for students to do in the beginning. And each week you might have a different way of helping students understand growth. You might have them think about patterns of growth that they can actually see, or they might think about growth in a representation such as a graph. And once you have these different kind of ways of thinking deeply about growth, then you can see how they all fit together to build their understanding of this broader learning goal.
So here are some strategies that you could use for unpacking a topic to create learning objectives. You might find someone else's objectives and borrow their ideas. Another thing is that the end of chapter summaries can be useful.
Textbook authors in physics have thought very hard about breaking the topical area down into chunks, and there's usually a summary at the end of the chapter. The textbook summary is usually mostly a list of formulas and definitions, but it's a good synthesis of what were the key ideas of that chapter.
Another thing to consider is that the education research could guide you.
It's often what educational research is doing is to try to figure out what are the elements that comprise the understanding of some topical area.
You can also work backwards from an exam question.
So I sort of ask myself, why that question? What am I really getting at? Once I move that one level back, then I can usually articulate a learning goal which could generate multiple exam questions, including the one that I had started with. Maybe it was one I'd given in the past, or one that a colleague had given, or a canonical problem from the textbook. But what you're really trying to do is ask, what is the essential underpinning idea or technique or skill that this question is getting at.
Lastly, you can talk to your colleagues to bounce ideas back and forth. Here's an example from Steve Pollock on Newton's laws.
So as a concrete example, I'm teaching, there's a chapter on Newton's laws in the textbook. It's a big topic in introductory physics, and the formula in the back of the book is F equals ma, or maybe F net equals ma. And so you look at that and you think, well, what are the learning objectives here? One is for a student to know what are the forces acting on an object. So you have to think about, what does that mean? Given, for example, a verbal or pictorial description of a problem, I want the students to be able to identify all the forces acting on a body. They need to decide what is the relevant body, because sometimes you have multiple objects interacting. So I want the student to be able to choose the relevant object and then identify all the relevant forces acting on it. I want them to be able to draw a picture, a representation. It's called a free body diagram. So these are all concrete skills, and they're all part of F equals ma, but they're the subparts, and I would like for them to be able to do those independently. And they are the essential skills required to solve any problem involving F net equals ma.
So now I want you to think on your own again. What's a topic you've taught? What goes into learning that topic? What are the component ideas and things that a student needs to do in order to be expert in that topic? So here's another opportunity for discussion. Once you've got some ideas about what goes into a topic, work together with someone else to further refine your ideas about the deconstruction of that topic. This is something, again, that's really helpful to do in combination with somebody else. Now, if you don't have somebody to work with, I do have an optional video showing some of our graduate students working through their ideas on deconstructing particular topics in STEM. So breaking down a topic into its components does take some practice. It requires that you tap into your deep disciplinary knowledge of the subject to realize what it means to understand that topic. But it also means that you have to step back from that disciplinary knowledge and expertise to remember what it's like to learn something for the first time. Now, in the next video, we're going to look at another way of analyzing the knowledge that you want your students to have.